Pappus of Alexandria was one of the last great Greek mathematicians of antiquity, known for his synagogia or collection, and for Pappus's hexagon theorem in projective geometry. Nothing is known of his life, except that he had a son named Hermodorus, and was a teacher in Alexandria. Collection. His best-known work is a compendium of mathematics in 8 volumes, the bulk of which survives. It covers a wide range of topics, including geometry, recreational mathematics, doubling the cube, polygons and polyhedra. Context. Pappus flourished in the 4th century AD. In a period of general stagnation in mathematical studies, he stands out as a remarkable exception. How far he was above his contemporaries, how little appreciated or understood by them, is shown by the absence of references to him in other Greek writers, and by the fact that his work had no effect in arresting the decay of mathematical science. Thomas Little Heath writes, "In this respect the fate of Pappus strikingly resembles that of Diophantus, dating. In his surviving writings, Pappus gives no indication of the date of the authors whose works he makes use of, or of the time at which he himself wrote. If no other date information were available, all that could be known would be that he was later than Ptolemy, whom he quotes, and earlier than Proclus, who quotes him. The Suda states that Pappus was of the same age as Theon of Alexandria, who flourished in the reign of Emperor Theodosius I. A different date is given by a marginal note to a late 10th century manuscript, which states, next to an entry on Emperor Diocletian, that, at that time wrote Pappus. However, a real date comes from the dating of a solar eclipse mentioned by Pappus himself, when in his commentary on the Almagest he calculates the place and time of conjunction which gave rise to the eclipse in Tybe in 1068 after Nabonassar. This works out as October 18, 320 AD, and so Pappus must have flourished c. 320 AD. Works. The great work of Pappus, in 8 books entitled Synagogia or Collection, has not survived in complete form. The first book is lost, and the rest have suffered considerably. The Suda enumerates other works of Pappus. Chi omega rho omicron gamma rho alpha phi iota alpha omicron kappa omicron upsilon mu iota kappa eta. Commentary on the 4 books of Ptolemy's Almagest. Pi omicron tau alpha mu omicron sigma tau omicron sigma nu lambda iota beta upsilon, and nu epsilon iota rho omicron kappa rho iota tau iota kappa alpha. Pappus himself mentions another commentary of his own on the nu alpha lambda eta mu alpha of Diodorus of Alexandria. Pappus also wrote commentaries on Euclid's Elements, and on Ptolemy's rho mu omicron mu iota kappa alpha. Collection. The characteristics of Pappus's collection are that it contains an account, systematically arranged, of the most important results obtained by his predecessors, and, secondly, notes explanatory of, or extending, previous discoveries. These discoveries form, in fact, a text upon which Pappus enlarges discursively. Heath considered the systematic introductions to the various books as valuable, for they set forth clearly an outline of the contents and the general scope of the subjects to be treated. From these introductions one can judge of the style of Pappus's writing, which is excellent and even elegant the moment he is free from the shackles of mathematical formulae and expressions. Heath also found his characteristic exactness made his collection a most admirable substitute for the texts of the many valuable treatises of earlier mathematicians of which time has deprived. Thus, the portions of collection which has survived can be summarized as follows. We can only conjecture that the lost Book 1, like Book 2, was concerned with arithmetic, Book 3 being clearly introduced as beginning a new subject. The whole of Book 2 discusses a method of multiplication from an unnamed book by Apollonius of Perga. The final propositions deal with multiplying together the numerical values of Greek letters in 2 lines of poetry. producing two very large numbers approximately equal to 2*1054 and 2*1038. Book 3 contains geometrical problems, plain and solid. It may be divided into 5 sections. On the famous problem of finding two mean proportionals between two given lines, which arose from that of duplicating the cube, reduced by Hippocrates of Chios to the former. Pappus gives several solutions of this problem, including a method of making successive approximations to the solution, the significance of which he apparently failed to appreciate. He adds his own solution of the more general problem of finding geometrically the side of a cube whose content is in any given ratio to that of a given one. On the arithmetic, geometric and harmonic means between two straight lines, and the problem of representing all three in one and the same geometrical figure. This serves as an introduction to a general theory of means, of which Pappus distinguishes 10 kinds, and gives a table representing examples of each in whole numbers. On a curious problem suggested by Euclid I-21, on the inscribing of each of the 5 regular polyhedra in a sphere, an addition by a later writer on another solution of the first problem of the book. Of Book IV, the title and preface have been lost, so that the program has to be gathered from the book itself. At the beginning is the well-known generalization of Euclid I-47, then follow various theorems on this circle, leading up to the problem of the construction of a circle which shall circumscribe 3 given circles, touching each other 2 and 2. This and several other propositions on contact, e.g., cases of circles touching one another and inscribed in the figure made of 3 semicircles and known as arbolos, form the first division of the book. Pappus turns then to a consideration of certain properties of Archimedes' spiral, the conchoid of Nicomedes, and the curve discovered most probably by Hippias of Elis about 420 BC, and known by the name of tau epsilon tau rho alpha gamma omega nu iota sigma mu omicron sigma, or quadratrix. Proposition 30 describes the construction of a curve of double curvature called by Pappus the helix on a sphere. It is described by a point moving uniformly along the arc of a great circle, which itself turns about its diameter uniformly, the point describing a quadrant and the great circle a complete revolution in the same time. The area of the surface included between this curve and its base is found, the first known instance of a quadrature of a curved surface. The rest of the book treats of the trisection of an angle, and the solution of more general problems of the same kind by means of the quadratrix and spiral. In one solution of the former problem is the first recorded use of the property of a conic with reference to the focus and directrix. In Book V, after an interesting preface concerning regular polygons, and containing remarks upon the hexagonal form of the cells of honeycombs, Pappus addresses himself to the comparison of the areas of different plane figures which have all the same perimeter. Incidentally, Pappus describes the 13 other polyhedra bounded by equilateral and equiangular, but not similar polygons, discovered by Archimedes, and finds, by a method recalling that of Archimedes, the surface and volume of a sphere. According to the preface, Book V is intended to resolve difficulties occurring in the so-called lesser astronomical works, i.e., works other than the Almagest. It accordingly comments on the Spherica of Theodosius, the moving sphere of Autolycus, Theodosius's book on day and night, the treatise of Aristarchus on the size and distances of the sun and moon, and Euclid's Optics and Phenomena. Book 7. Since Michel Cazals cited this book of Pappus in his History of Geometric Methods, it has become the object of considerable attention. The preface of Book 7 explains the terms analysis and synthesis, and the distinction between theorem and problem. Pappus then enumerates works of Euclid, Apollonius, Aristaeus and Eratosthenes, 33 books in all, the substance of which he intends to give, with the lemmas necessary for their elucidation. With the mention of the porisms of Euclid we have an account of the relation of porism to theorem and problem. In the same preface is included the famous problem known by Pappus's name, often enunciated thus: having given a number of straight lines to find the geometric locus of a point such that the lengths of the perpendiculars upon, or the lines drawn from it obliquely at given inclinations to the given lines satisfy the condition that the product of certain of them may bear a constant ratio to the product of the remaining ones. The theorems, which were rediscovered by and named after Paul Goldine, but appear to have been discovered by Pappus himself. Book 7 contains also under the head of the dissection a determinator of Apollonius' lemmas which, closely examined, are seen to be cases of the involution of 6 points. Important lemmas on the porisms of Euclid, including what is called Pappus's hexagon theorem, a lemma upon the surface loci of Euclid which states that the locus of a point such that its distance from a given point bears a constant ratio to its distance from a given straight line is a conic, and is followed by proofs that the conic is a parabola, ellipse, or hyperbola according as the constant ratio is equal to, less than or greater than 1. Cassels's citation of Pappus was repeated by Wilhelm Blaschke and Dirkstruck. In Cambridge, England, John J. Milne gave readers the benefit of his reading of Pappus. In 1985, Alexander Jones wrote his thesis at Brown University on the subject. A revised form of his translation and commentary was published by Springer Verlag the following year. Jones succeeds in showing how Pappus manipulated the complete quadrangle, used the relation of projective harmonic conjugates, and displayed an awareness of cross ratios of points and lines. Furthermore, the concept of pole and polar is revealed as a lemma in Book 7. Book 8. Lastly, Book 8 principally treats mechanics, the properties of the center of gravity, and some mechanical powers. Interspersed are some propositions on pure geometry. Proposition 14 shows how to draw an ellipse through 5 given points, and Prop. 15 gives a simple construction for the axis of an ellipse when a pair of conjugate diameters are given. Theorems. Although Pappus's theorem usually refers to Pappus's hexagon theorem, it may also refer to Pappus's centroid theorem. He also gives his name to the Pappus chain, and to the Pappus configuration and Pappus graph arising from his hexagon theorem.